Hi, everybody. Today I'm going to talk about understanding the flip-flop by PSPICE. Simply, I just um, talk going to talk about the flip-flop, but to get a better pictures, I'm going to use the PSPICE student version to explain or to show you or also how the flip-flop work. Even we already understand about the truth table or the how to get the output what is the output is going to be by having a different input um, which mean we have preset, we have clear, we have clock, and we have D as the data input. And if you look at the PSPICE, which I already have sorry here, also have the 747 as their D flip-flop, and I also draw the equivalent circuit diagram for the flip-flop to explain more. Okay, we get into that, but let's start with the truth table for the flip-flop. You take a look back at the D flip-flop. You can see that right here we have uh, 6 pins which have our clear, clock, data, preset, Q, and complementary Q complementary. So this is mean if Q become 0, this one is going to be a 1, or if Q is 1, is Q complementary is going to be 0. And actually this is the clock that we will change the status of the output, which are here is the Q and Q complementary, and clear is worked by if you have the digital logic to be 0 when your preset have a digital logic 1 is going to clear the output Q to be 0 and Q complementary to be 1. That's what we call asynchronous clear. This means it's going to clear the output to be 0 right away. And also for the preset, it's worked by digital logic 0. It's the same thing if we have the digital logic of the preset to be 0, is worked by 0. And the clear pin is there, has the digital logic to be 1, is going to preset the output to be 1. And but in the case of preset and clear to be 0 at the same time, this is we call illegal. That means you're going to have a Q and Q prime, Q complementary to be 1 or 0 at the same time. So that's make the system confused. That's why we call illegal operation. Okay, so let's get back to the truth table again here. So I leave this one out, Q and Q complementary. Just we're going to fill this up together. Let's start with the for the, as I mentioned earlier, if you just take a look at their digital status of our clear pin, if it happen to be 0 0 when preset is become 1 1 1, so you take a look only this part here, you know exactly that clear pin is worked by digital logic 0, so it will give you the output um, Q all to be 0. So you have R 0 here, right? And your Q prime is going to be or Q complementary is going to be 1 1 1. And for the preset is 0 when the clear pin is have the digital logic to be 1, is going to give your output this one to be 1 1 1 1, and Q complementary is going to be Q to be 0 0 0. And this one I have 4 inputs, so I have the combination to be 2 to the 4th, so let's make our 16, right? So that's why I have our 16 combinations. Just to make it clear, I don't have to write down all of the digital logics like this one, but just point you out. Okay. And as I mentioned earlier, when both preset and clear pin has the digital logic to be like 0 0 here, so this is what we call our illegal operation. So this means we not really use this combination to have output, because this one is going to give you, or you don't know, it's either going to be 1 1, because your preset work by 0 is give you 1, right? But you also have clear becomes 0, so this one you don't know which is going to be 1 or 0, so that's why we call illegal operation. So it's left off only this part of combination. So your both preset and clear is there are like 1, digital logic 1, right? And now you take a look at this one here. Now it's depend on the clock, and since the flip-flop is going to work, change your output status by the leading edge. This is what we call a leading edge. So it changed digital logic from 0 to be 1, not this one here. This one we call a trailing edge. It changed the digital logic from 0 to be from 1 to be 0. Okay, so your output is going to change corresponds to the data pin here. You have to take a look at the clock. If I put this one 0 is mean says change the digital logic from 1 to be 0, it's not going to affect your output. But if you have a digital logic of the clock change from 0 to 1, or this is the leading edge, right? It's going to change your output status or Q here. Okay, so we will go to see the PSPICE. Okay, what I have here is the PSPICE, and this is a getter part of 7474. You still remember, you simply control G to get the part, and you type in 7474. So this is your D flip-flop, and this is equivalent circuit. I have 4 NAND gates, 1 2 3 4, and also 1 inverter, which is I have used number 7400 for the NAND gate, and for the inverter I used 7404 for inverter. And for the input signal, the digital input signal, I used the digital clock. Okay. And the way I set up, just take a look at this one here first. As I told you, if I want to see how Q is going to change according to the clock signal is coming in, which I told you is it will be tricked by the leading edge of your clock, right? When your preset and your clear pins as the digital logic to be 1, otherwise not going to work. Otherwise it's going to be like clear or preset your output. Okay, your preset work by 0. Just give you output to be 1. I mean, in this case is Q. And for your clear pin, it's work by 0 as well. But it's going to give your output Q here to be 0. Okay, so we just take a look at the clock pin when the preset and clear is connected to digital logic high. Okay, so that's why I set up the way I set up the digital logic of preset and clear to be high only. I simply go to sorry for, just wait a minute. I have attribute somewhere. Oops, I have to clip this one. Let's just make sure it's look right, and I go to attribute. See, I have on time to be 1 second and off time to be 0, so it's no off time. So I have like the signal here to be digital, give you a digital logic to be 1 only. And for the clock, the way I set up is that I set it on time to be 0.5 microsecond and the off time to be 0.5 microsecond. And then for the data pin D here, I just set it up to be on time 2 microsecond and off time to be 2 microsecond, so I can see your output according to your data pin and your clock. So just take a look at this quick, right? I'll see if I change this one to be clock, and sorry, this is to be data pin. Let's say this one attribute, change this one to be D1. Let's say data 1, right? And this one, just for reference, change this one to be clock. Okay, since I have this data pin with the period of 2 microsecond plus 2 microsecond, so I have like the period of 4 microsecond. I'm going to set this one set up to get the plot. Go to transient. I can put just like 12 microsecond, and then you close, and then you go to simulate. I just going to show you how it look like. So this is what I have data 1, right? And then you click this one to see your clock signal here. So this is what's happening. I just want to see how the clock going to trick your data pin to show up at your output queue here. Okay, so it seems we already have everything right here, and if you want to see the digital logic of preset and clear pin, you can also go to let's change this one to be something else. I put attribute. Okay, doesn't matter. So let's take a look at the STM1. I should have the logic or digital to be 1 all the time, right? This is my DSTM1. See, this is have the digital logic to be 1. You can also put the display or your cursor here. You can see it's tell you the digital logic at any particular time on the plot. So my preset and clear always have the digital logic to be 1. Now you want to see your output here, Q. You add more plot. Sorry, I'm on U2A, so we go to U2A Y. This is the it's already have because it's the flip-flop. So I have the output of U2AQ. I can see here my output, and then also you go to Q or complementary. So go to Q2A Q bar. Okay, and you can see your Q and Q complementary always to be your invert of each other. So I have for Q I have digital logic here to be 1, but for Q complementary is become a 0, and this one I have Q with the digital logic 1. I have Q complementary to be, sorry, this is the 0, right? And then I have the Q complementary to be 1. Now let's take a look at your clock coming in. As I told you, is going to trick by your leading edge, or when you have the logic of your clock, let's go from 0 to be 1, but from this point here, for the data pin is coming in here, is becomes 0, and then is changed digital logic to be 1. But when you have no clock, the leading edge coming in, you don't have the Q status to become 0. So this is your Q, right? So it still becomes 0, 0 until the leading edge of your clock is coming in, is going to change your output status Q from 0 to be 1. You can see at this point here, right? You compare together, and since your data pin still have logic 1, so it doesn't change the status, and now it changed the digital status, digital logic from 1 to be 0. So you have to wait for the clock until you have the leading edge is coming in. At this point, it's going to change your output status Q to be 0, as you can see from here. Okay, so this is how the D flip-flop work. And you also can play around with the your preset and your clear pin to be something else. I mean the digital logic. When you want the for example, you want to have a clear pin to be 0 here when your preset as the digital logic um, 1, right? You want to see if your Q uh, is clear to be 0 or not. And also I connect the circuit just to represent D flip-flop like this. And then if you want to check again, or I have this is my data pin, right? And this is my clock. It's exactly the same thing here, because with the data with period of full microsecond, and the clock with the period of square wave 1 microsecond, I can check that at the output here is actually Q, and this is the give you Q prime. So if I take a look at the U10A, this is the input A, input B for the NAND gate, and this is they call output Y. I take a look at the output of U10A. It should give me the same as the output of U2A. Okay, so take a look at the U10A Y. I add this one, U10AY, I have right here. So this is exactly the same as the U2AQ, right? Okay. Hopefully this help you a bit about how our D flip-flop work.